So today we are going to talk about the two generals problem. Two generals problem. It's also known as the two generals paradox, or it's a well-known problem in computer science that also has major implications in practical applications. So just to state the two generals problem in words, this will be like the more specific version, but we'll generalize it later. So two generals communicating over an unreliable channel of communication. Two generals communicating over an unreliable channel will never come to a consensus or agreement with 100% certainty. So basically we are saying if there are two parties, two generals communicating over some unreliable channel, basically we are saying an unreliable channel is something where the messages that are being sent can be lost. So that's a communicating over an unreliable channel will never be able to come to a consensus. The two parties will never be able to agree with 100% certainty that they are both agreeing on the same thing. So basically we are saying that, let's say this general will never be certain that the other general has agreed, will never be 100% certain that the other general has agreed to a certain thing, and it's the same the other way. So to make it more concrete, we can start with the scenario. So this is let's say a small depiction of the two generals problem. So we have general A with their army over here, and then there is general B. With their army over here. And let's assume that this is there's a hill in the middle between the two generals and their armies, and there's a dangerous forest in the middle. Okay, so the two generals are trying to communicate and agree on whether to attack an enemy that's over here, an enemy army that's somewhere else, whether to attack this enemy army. So basically, if General A tries to attack by themselves, they know that they will get lost, and General B knows that they will get lost if they try to attack by themselves. So they want to combine their forces and then attack the enemy. So they want to come up with a time and attack plan before they can attack, before they decide to attack. So yeah, so then so basically what General A, let's say General A wants to start the conversation. Let's say General A is this. General A sends a message, starts a message saying, let's attack at dawn. So General A writes a message saying, let's attack at dawn. And like in old times, they will have some kind of a messenger carrying this letter saying, let's attack at dawn, and carrying this letter. And what they're going to do is, this messenger will be traveling through the hill, through this dangerous forest, over to General B saying, let's attack at dawn. So from the perspective of General A, can they know whether to get their army prepared, or should they just be waiting until they hear back from General B? So it can be either way, but usually it would be that General A would send the message, and they would want to hear back from General B saying, okay, let's attack. Otherwise, they will be moving their forces and making some major arrangements, which might be costly or something. So they may not want to start their processes for the attack until they receive a confirmation. So the main problem here is that this path that this messenger takes, this is very dangerous. So that means the messenger and the message can get lost in the middle without anyone knowing. So that's why we are saying this is an unreliable mode of communication, unreliable method of communication. So in this hypothetical scenario, this messenger can get lost in this forest, and this General B would never know that General A even sent a message. That's a possibility. So if the message got received by General B, what General B is going to do is it's going to send another message back saying, okay, to attack at dawn. Okay, to attack at dawn. So okay, and then once General B gets the first message, they will write a new message saying okay to attack at dawn, and send it back over to the General A. But now General A knows, okay, now General A knows that General B has received a message saying let's attack at dawn. But there's a problem. General B is not sure that this message that they sent, this number 2 message that they sent was ever received by General A. So now the General B may want to, before they start making arrangements to move their army, they may want to hear back some kind of acknowledgement from General A. So if we go to a new page, let's say this is the time, and this is the General A, and then there is General B. So they will say first message is let's attack at dawn. This message gets sent to General B, and when they received it, when General B receives this message, they write a new message saying okay to attack at dawn. And then this message, assume these lines are the going over the hill, messenger going over the hill. So it takes some time for a message to go from one army base to the other, one army base from here to here. So when General A sends the message, General B receives the message, and then B sends the second message back to General A. Now since B, like we were saying, B is now wondering whether their message was ever received by General A. So they want some kind of acknowledgement. So what General A is going to do is, once they receive that message, they are going to say okay to attack at dawn. And they are going to send that message through the hill with the messenger until General B receives it. Okay. Now at this point, when the General B receives the message, they know that General A received their second message. So just to illustrate, if we look at from here to here, in this time, after General A sends the first message and until General A received the second message, A is uncertain what B is thinking. Whether they are not sure whether B received the message or not. And in the same way, while General B sent the second message and until B received the third message over here, they are uncertain whether or not A received their message and what's their plan. So, and then coming back, so it's again. So General B now knows that their second message was received by General A. But on the other hand, General A, who sent their third message, doesn't know if General B received this third message, which said, okay, that I received their second message. That means General A is now expecting some kind of message from General B saying, okay, I received your message. So there will be number 4th message saying okay to attack at dawn. And then 4th message gets sent over to General A. So as you can see, there's going to be some kind of a loop. Basically, whoever sent a message will never know that the other party received the message and processed the message. So until this 4th message came to General A, they don't know whether B is certainly agreed to that message. So they are uncertain until this point. And it will again be all over the same thing, because now A will say, now A knows that it received the message, but B doesn't know if their 4th message ever got received by General A. So it will be General A's responsibility again to say, okay, I want to attack, I received your 4th message, just to say to general B, and then again there will be another message saying okay to this and that, and then it needs to be sent over this side. And then so during this time again the general B doesn't know what happened, and it will go round and round with both of them sending messages back and forth, saying acknowledging whatever they acknowledging that they received the other person's last message, and that will never end. So the general A, once they sent one message, let's attack at dawn, and general B, once they receive the first message, say let's attack at dawn, and then the second message, okay to attack at dawn. So once they send the second message to general A, general B wouldn't want to prepare their army until the acknowledgement for their second message got received, because that message can get lost. So it's the same thing that's getting happening all over again. 3 gets sent, and once general A sends number 3, they don't know if that 3 got received by general B, so they want some kind of acknowledgement, and they receive some kind of acknowledgement from B. So until that acknowledgement is received, they will not prepare the army, because they don't know if general B has agreed yet. So it will go again and again in a loop. So just to give so that's the scenario in the two generals problem. So to give a generic definition, generalized definition for the two generals problem is two parties communicating over an unreliable channel, will never come to a consensus with 100% certainty. Like we were seeing previously, that's because whatever they send, they are sending saying okay, I agree. If one person says okay, I agree, the other person, the person who is sending the last message, don't know if that message went through or it got cut off in the middle. So they always want another acknowledgement, and then this acknowledgement can get go through or can get cut off. So it will keep, there will be always be a new expectation from the other party to send a message saying acknowledging the message. Okay, so this seems like a very hypothetical situation, but it has very real world implications. So let's look at one of those. So let's say we have a ATM and a bank server that's far away. So this is the time. Okay. So the ATM and bank are communicating over a network. So if we think about this network, usually they are far away in some physical locations. They are far away, and there are so many components, network components in the middle, and these things can go wrong, and there can be all kinds of issues that can happen in the middle that will cause the messages to get lost in between. And that's pretty much the same as our hill with the dangerous forest in the middle. This is a unreliable mode of communication. Any kind of network is supposed to be an unreliable mode of communication, because let's say even our Wi-Fi gets disconnected. Your mobile phone has disconnection issues. So even the ATM and bank are using the almost same kind of infrastructure, and these infrastructure can break down. Okay. Just clear that part out. So we agree that there's an unreliable mode of communication. So that means this is almost the same as our two generals problem. So these two trusted parties that are trying to communicate over this unreliable channel, and they are trying to agree on something. Say there's a user called Alice wants to withdraw $50. Alice wants to withdraw $50, and the ATM needs to come to an agreement with the bank whether to release this $50. So okay, let's say this is our first message. This numbering has a small first of all, it helps to describe the situation, but also this having this kind of numbering is actually having some kind of ID is a feature that's usually useful in this kind of setting that we'll discuss later. So when Alice sends a message to Alice goes to the ATM and tries to withdraw $50. And the ATM is gonna send this message, Alice is withdrawing $50 to the bank. And ATM wants to know from the bank whether it should be allowed. And if that's allowed, then they can release this $50. So this message gets sent over to the bank. And the bank sees this message and says, okay, it will try to verify this message, verify whether the Alice has enough money, those things, and then it will say okay, Alice minus 50. Okay, so it's saying okay, I got the message and I'm ready to subtract $50. And then this message gets sent over to the ATM. So while this first message went to bank, and then the bank sends the second message. So just like the two generals, the ATM, until this second message arrives, it doesn't know whether the bank agreed. ATM doesn't know whether the bank agreed. But when the ATM receives the second message, it knows that okay, the bank said okay, so that's ready. But the problem over here is now the bank doesn't know whether to actually reduce the 50 because reduce the 50 from Alice, because it doesn't know whether this second message went to the ATM. So it's expecting a message back from the ATM saying, I received your second message. I'm going to be releasing $50. So it's expecting this kind of message. Let's write it simply. Okay to say number 2. So they will send this message and then get this message over here to the bank, and then the bank, once the bank receives the okay to number 2, it's saying, okay, it has some kind of information. So until this message was received, bank doesn't know what the ATM was thinking. What's the status of the ATM? And similar to our two generals, now the ATM, after they sent this okay to number 2 message, they don't know if the bank ever received this okay to number 2 message over the wire, over this unreliable method of communication, saying okay. So let's say let's say that they released the $50, but this message didn't go through. That means Alice got free money. That's good, but that's good for Alice, but not good for the bank, because the money is lost in the middle, and the bank never knew whether the $50. The bank would think that the $50 wasn't withdrawn. So now the ATM sends the okay to number 2, and then so the ATM, just to be sure, it has to wait until the bank says okay to number 3. So until the ATM receives this message, it doesn't ATM doesn't know whether the bank agreed to do this transaction. And now the problem goes back to the bank. Bank is thinking whether number 4 went through, and then it's again the same thing over and over again. Basically, they are going back and forth in the loop, saying okay to their last message and acknowledging, and then waiting for acknowledgement from the other side without ever stopping. So this is a real world scenario that can happen because networks are unreliable, and these networks are unreliable, and it practically there's no way for us to make a 100% reliable network map of communication. So this seems rather depressing, because this seems like a real there are real applications that need to communicate and come to a consensus, but there's no way for two things to come to an agreement in this kind of situation. But in engineering, this is a theoretical impossibility. In real world, so basically in engineering, we can develop systems that have a certain, not 100%, but certain certain possibility of coming to a consensus. Possibility of consensus. So the theoretical impossibility says that never 100% consensus. 100% sure about the consensus. But when we are engineering a system, we can develop in certain ways such that they are almost we are almost sure that they have agreed on, that the two parties have agreed on a certain condition, certain event, or certain decision. So we have to discuss some kind of solutions. There are a couple of practical solutions that might work, but we have to keep in mind that these are not 100% solutions, because this theoretically impossible, but we can have some kind of some certainty that this will work. So one solution is a costly solution. Let's say we have the general has so many messengers that they can sacrifice to send a message. So let's say this general is, instead of a general A, instead of sending one messenger like we sent last time, instead of one messenger, they will send hundreds of messengers. They will send lots of these messengers, so that at least some of these messengers will be sent over to General B, hoping that at least some of them will get through. So that is one kind of solution. And if General B receives, let's say General A sends 100 messengers and General B received 95 messengers, that means this method of communication is almost from General A to General B. General A to General B has like a 95% reliability. But as you can imagine, this is, in this general's case, this is costly, because it will be costing in terms of their army. These messengers could have been the general in part of the general's army instead of being messengers, or they might, if the forest is too dangerous, it's also a possibility that they will lose their lives. So it is a very costly solution. And in the case of our ATM and bank, or in some other kind of distributed system scenarios, sending this or sending so many messages means we are going to take a lot of the bandwidth allowed for us. Say we have this amount of network bandwidth and we are sending so many packets of message packets, and there's not enough space for the data. It won't be not enough, but we are sending so many messages, and this and bandwidth is costly. So this is the bandwidth. Taking up so much space just for sending messages for reliability is a costly solution. But that's a solution because it gets around the fact that some messages can get lost. Another solution that's commonly used is a time-consuming solution, but it's more like, it goes like this. So A sends a message saying so this is A sends, this is the second solution. It's a time-based solution. So A sends some kind of message to B, and what B does is B will send acknowledgement for number 1 back to this guy, back to A. And this is the difference here, is that we know we can make an estimate on how long it would take for a message to go from A to B and B to A. So we have some kind of, we know the latency for a message to go from one end to the other. So what A is gonna do is it will wait for a certain amount of time until, let's say, for this round trip of a message, and if it didn't receive any kind of this acknowledgement from B, it will resend the message. It will keep resending the message until an acknowledgement is received. And what will happen here is that now when this number 2 is received by A will stop sending these new messages. When A stops sending the new messages, B will know that A has received the second message because A has stopped sending messages. And that's the second time-based solution. So in real world, these two solutions can be adapted in different formats to achieve practical solutions. So let's say for our ATM example, so in the real world, what happens is actually there are a lot of processors around, even like the ATM and the bank situation. There are a lot of processors around withdrawal of money or some different situations, so that we can have a if there are issues, that issues can be circumvented without major problems affecting the whole system. So for example, in an ATM and a banks will usually have some kind of withdrawal limit on how much money can be withdrawn at an ATM. Withdrawal limit on how much money can be withdrawn at the ATM. So the potential loss for a bank at the moment is very low. And if in the case that someone was able to get around this withdrawal limit, then there's the fact that if the bank balance goes withdrawal, so clear current page. No. Is processes in place. So this another solution, processes in place to work around the issues that can come up due to this problem. So in ATM and bank situation, there are withdrawal limits to prevent potential major losses, and then if bank balance goes negative, the bank will charge an extra fee until the balance is up. And also if there are some issues there between the ATM and the bank, if there are network issues, then they will be monitoring and alarming situations. And alarms. These are not like fire alarm kind of alarms, but this is like a big red button coming up in the red light coming up in a dashboard on some kind of system saying there's a network issue. There's a network issue between two components of the system. So these are the different solutions that are in place to get around a problem like this, because it is actually impossible to solve the problem of coming to a 100% consensus. So that's pretty much it for the two generals problem, and something to think about for the next time is what happens if in the two generals case, the general A and general B as with the two armies. What happens if the path that the general A and general B has to the messengers have to take can be intercepted by the enemy? What if the enemy was at the top of the hill? And these messages can, what if messages can get corrupted? What if messages can get corrupted? So that's something to think about for our next time on these kind of distributed systems.